This is video 27.1 where we look at the basics of electric circuits. Most of this will be review, but you probably still need to hear it anyway. Now the first thing is the definition of electric current, and that's the rate at which charge moves past a point. The idea is that we have a wire which has charge carriers, which we know in normal materials, meaning not semiconductors, are electrons. And those electrons have thermal motion. They bounce back and forth randomly. But if you apply an electric field, so positive here, negative here, what happens is that all of the electrons drift in the opposite direction of the electric field. So they're bouncing around. So if we look at this electron here, its path will look something like this. It bounces around a lot, but on the whole, it ends up moving in the opposite direction of the electric field. And there's a lot of electrons doing this, and so all told, if you look at a cross-section of the wire, let's say that, and you count how many electrons pass through that per second, you can compute the total charge that passes through that plane every second, and that's the current. So a way of writing it is I is Q over T, or sometimes we write it as dQ dt. And we know that electrons, in metals at least, are the charge carriers, they're the moving charges. But for historical reasons, we say that current is the movement of positive charge. In this case, the electrons are moving this way. But it turns out that that's equivalent to positive charges moving the opposite direction. So in this case, we would say that the current points to the right because the electrons are drifting to the left. And for everything you're going to see in circuits, positive charges moving to the right is entirely equivalent to negative charges moving to the left. Now the next idea is resistance, which we define as the ratio V over I. So if you've got some circuit element here, and you have a voltage across it, and a certain amount of current moving through it, the resistance of that element is V divided by I. There's also the concept of resistivity, which your book develops in great detail. You should have a look at it. But the main thing you need to know is that resistivity is a material property, meaning everything that's made of copper has the same resistivity, everything that's made of iron has the same resistivity, everything made of silicon has the same resistivity, and so on. And you can construct a resistor using the idea that the resistance equals resistivity times the length of the cylinder you're using divided by the cross-sectional area. The idea here is that you have a chunk of material. The resistivity rho is determined by the material. There's a table of different values in your textbook. And A is the cross-sectional area. So the idea is if current is flowing that way, it's the area of the face perpendicular to the current. And L is its length. And then the last thing associated with resistance is the difference between ohmic and non-ohmic devices. For ohmic devices, which means resistors mainly, the resistance is constant. In other words, the V over I ratio is the same for every value of V and I. Non-ohmic devices, which includes basically everything that's interesting, diodes, light bulbs, transistors, have a non-constant resistance. So for instance, if you plotted an IV curve, where you plot I versus V, for an ohmic device, you'd get a straight line. A non-ohmic device, for instance, a light bulb, would have a curve that looks like that. A diode, which is another kind of non-ohmic device, would have a curve that looks like that. So an ohmic device is going to have a linear IV curve. Non-ohmic device will have something other than a line. Now the last thing for this video is the concept of power in electric circuits. Now you probably remember power equals current times voltage. But where does that come from? Now remember the definition of current, charge per unit time, and the definition of voltage, which is energy per unit charge. I should use something other than E for energy. Let's try using U. Now the idea is that if you've got a circuit element that has a voltage V across it, what this means is that the amount of energy carried by each electron, or the energy lost by each electron, really, is equal to Q times V. But there are a certain number of electrons per second, and so I times T is the total amount of charge. And so the total energy in time t is equal to I times T times V. And the power is energy per unit time, so it's energy divided by time, and that equals IV. So that's how it's derived. The AP exam says you are required to derive that equation. Hasn't shown up on any exams recently, but it's a good thing to know. That it's not just, magic and I told you what the equation was and now you remember it. Now the next question is, how do we interpret those equations? Because you can calculate I times V for anything, but you need to know what it means. Now if you've got a resistor, I times V is going to be the rate at which electrical energy becomes heat. Because what the resistor does is it takes the energy the electrons have and it turns it into heat. A resistor will heat up, not always perceptibly, but it always has some increase in temperature. If you've got a battery, that's the rate at which the chemical energy in the battery becomes electrical energy. If it's a light bulb, it's the rate at which electrical energy becomes light and heat. But think about that whenever you're asked to calculate the power of an electrical device. Now tomorrow I'm going to check all of the questions in chapter 27. It's all review. You should not have trouble with these. And in fact, that video is all of the material you need to know from chapter 27.